Alright, so we got about 2 more minutes before we start. And I just got home, well, maybe, within 15 minutes, because I was having a tour of the STEM building, which is kind of where we would have been if it's not for COVID-19. So I was going through all 3 floors, all of the classrooms, all of the labs, the Mesa STEM base, um, and my own office. So it was kind of cool, going through the new building. It's definitely one step up, from definitely one step up from the portable buildings, but it's also one big step up from liberal arts for those of you who have been on this campus for long enough. So I'm not really sure how many of you would actually end up taking classes in the STEM building because we are most likely going to be online in fall 2021. So spring 2022 is going to be the first day that the first semester that we might actually teach classes in the new building. So there's that. Um, so I'm just looking at the text channel. I'm not seeing any questions, any comments. So those of you who want to ask questions, we still have about 30 seconds to ask out of class, type of questions. Otherwise, we'll get the class started in another 15 minutes or so. All right, so we got some questions. Very good. All right, so Daniel, you might want to mute your mic. Thank you. Okay, so to address the first question, do I think there will be a support for the infrastructure for online-based learning after pandemic? That's probably going to continue, because we already have a lot of classes, being taught 100% online. The CISP faculty, people who teach CISP classes, we collectively do not want to continue teaching classes online, so we'll be moving back to at the most 50% hybrid, and many of us, want to do 100% on campus, on site, face-to-face teaching. And the science people and the math people, basically share the same, uh, they share the same opinion. So it's not really just CISP that's going to be going back to face-to-face. Many other departments will also be going back to face-to-face if it is when it's safe and possible. Yeah, yep, new building. So, and once again, I'm not really sure how many of you will continue to, will still be here, at ARC in spring 2022, because that's going to be the earliest semester that I think, realistically speaking, that we'll be moving back into the actual classroom. Even though the fall 2021 schedule is scheduled physically on campus, but there's a very, very good chance that we will probably go online in fall 2021. So it all depends. A lot of dependency that we do not know yet. All right, so Dawood is still typing, but I'm gonna move forward with today's material. So last class on Monday, we talked about resolution as a really cool mechanism to remove mentioning of variables. The question is, did I get my shot for COVID-19? I got the first shot, and then I'll get my second shot on the 30th of this month. But it's not going to be helpful until everybody, including students, get their shots, right? So just me getting my shots is not going to help when it comes to getting back to face-to-face teaching. So anyway, so what we'll do today is we are continuing on to talk about proof by contradiction today. So proof by contradiction is a very powerful technique of proving, and I know it sounds kind of intuitive. So we'll go ahead and go through that first. Okay, we'll basically show why proof by contradiction works, and then we'll kind of connect proof by contradiction with everything that we have talked about so far. So when you look at this derivation, this is actually a pretty good exercise, for those of you who want to kind of get some hands-on experience, to practice your Boolean algebra, because every single derivation between the rows is based on one or another rule of Boolean algebra. From the first to the second, all I did was to convert the implication into a negation and then followed by an or. And the same way over here, but this overall implication is not changed. And then over here, I applied the same thing, to the overall implication. So this particular implication becomes a or, but the precedent has to be negated, and that's why you see a negation over here. And then from here to here, from the third to the fourth row, I applied DeMorgans Law. So by applying DeMorgans Law, the outside negation, which is the one where the mouse pointer is quote-unquote distributed to the inside. So this P here is technically not P, because we have one not that is being distributed, and it already has its own negation. So this is supposed to be not P, but I did a simplification because double negation cancels out, so we just get P left. The Q did not end up with a negation to begin with, so when we distribute the negation, it now gets its own negation. And the application of DeMorgans Law changes a or to an and after the distribution. So that's how DeMorgans Law work in this case. And then on the other side, I just applied the associative law, which basically means when you have nested disjunction, it really doesn't matter which one you do first. So the parentheses dissolves. From here to here, I applied, let me check. From here to here, I dissolve the parentheses again. So this time, I dissolve this pair of parentheses, starting from here and ending here. So that pair of parentheses dissolves, and once again, it is the associative law of Boolean algebra. And then once we dissolve everything, I reverse, and introduce a true, with an and, because true is kind of like 1 in multiplication. When you look at true in the context of a conjunction, it's the identity. So anything and true is just the original anything. And I did the same thing with not R. And then from here to here, I look at 1 and go like, how else can I express true? So true is basically an expression or the negation of the same expression. So in this case, I specifically choose to use Q. Q or not Q is always true. So I basically replace the true with this kind of expression. And the same thing over here, this true is replaced by Q or not Q. And then from here to here, I use distribution, so that I distribute the Q or not Q over not P. So now we have not P and Q, or not P and not Q. And then I do the same thing with this one. So now we end up with a fairly long and complex expression. And then from here to here, I reordered the conjunctive elements. So this form, by the way, this form here is called DNF, or disjunctive normal form, where the overall operation is a gigantic or, and then each component I am oring is a conjunction. And then from here to here, I explained that already. From here to here, it's just a reordering. And then from here to here, I combined. Okay, so I skip a few steps. I skip a few steps here. From here to here, it is factoring. because we can see how the first and the second expression, they both have and not q, as the second part. But the first part, one has p and the other one has not p. So we can now use factoring. So it becomes p or not p, the whole thing, and not q. And that's why we have the 1 over here. And then we do the same thing over here, where we have q and not r, or q and r. So when we do factoring, it becomes q and in parentheses not r or r, and that becomes true, and that's why we have q and true over here. And then I skip another step too, because 1 and whatever is just whatever. So we end up with not q. This whole thing becomes just not q, and then this whole thing becomes just q. But because we have the negation of q in an or, and then we also have q in an or, those two combine to become just true, and as a result, we just have true down here. All right, so I'm getting back to the text channel. So the identity is already introduced in the previous class. So if you go back to the previous class, I gave you a bunch of rules, right? Okay, let me switch to the tablet first. There's my tablet. There we go. So this is coming from the previous class, and in the previous class we can see how identity works. Right here, a and true is just a. Now a doesn't have to be a single variable, it can be really a long complex expression. So basically anything and true is true. That is identity. So true is identity with respect to conjunction, and then false is identity with respect to disjunction. All right. So, and then Aiden asked, is it possible to derive these steps with a computer? The answer is yes. Okay, so the answer is yes. The problem with using a computer to derive these is not so much the computer doesn't know how to apply, because it's also kind of syntactic operation. The problem is the computer cannot decide which rule to apply next. Okay, because at any point there is a huge number of rules that can be applied, and then the computer doesn't really have the experience, to know, okay, which way should I go, right? And even people with, people who are just getting introduced to Boolean algebra probably will have to spend some time, okay, to figure out, what rule should I apply. I mean, it is counterintuitive that I am, I'm making an expression more complex by saying, oh, not p is not p and true, and then the true becomes q or not q. That is totally counterintuitive, because I turned something that was simpler into something that becomes more complex. So the answer is yes, it is possible, but proving theorems like this using algebra, using a computer, especially with longer and complex ones, may not be feasible. Okay, so it's possible, but it may not be feasible. I'm not really sure about the state of the art engines for proving theorems, so I cannot say for sure. But it kind of gets back into what we talked about earlier, that the space is infinitely large, and we're looking for a needle in the haystack. So it's sort of like that, because if I don't tell you that this eventually becomes true, then we don't even know whether it's going to be true or not, right? So that becomes the other issue is, are we just not getting to true because it really is not true, or are we not getting there yet because we kind of use some derivation and headed out in the wrong direction? So there's always that. All right. So now the bottom line is, what does that mean? Okay, P implies Q itself implies P and R implies Q and R can be anything in this case. So that really is the question. Why is this useful? Okay. So what I'm gonna do is, on the tablet, I'm gonna start a new page. You can't see it yet because I'm still setting it up, and I'm going to just mention this. P implies Q. I'm just copying onto the tablet at this point, and then because it's probably going to be useful to refer to this at some point. Okay. And I can show you what I have on the tablet right now. It really is just a copy of this. It's not by itself so much of a theorem. This is more like a corollary, which is a small theorem. But nonetheless, it is a statement. Okay, it is a statement. So what this means is if you can convince me that P implies, okay, let me switch back to the tablet. So this means, you know, if you can convince me that P implies Q itself is true, then it doesn't matter what R is, okay? Because P and R implies Q and R is also going to be guaranteed to be true. Yes, Damon is correct. We can, in fact, use a truth table to prove the whole thing. So this is going to be an exercise for you guys. Now, it's optional because I don't want to grade this, okay? But it is optional. So what you want to do is to set up a truth table where you have 3 independent variables, P, Q, and R. And then you basically look at each row. There will be 8 rows because, you know, each one can be a true or false. So 2 to the power of 3 is 8. So there'll be 8 rows. So what you want to do for the 8 rows is to actually compute the value of this entire expression, given that P, Q, and R have their specific, you know, values for that particular row. And what you will find, okay, so you really should do it if you are curious, but what you will find is every single row will end up with a 1. So it's going to be 8 ones with this particular truth table. So that means it doesn't matter what we choose as P, Q, and R. This particular statement is always true. Okay, it is just always going to be true. And Yolanda is typing something. So when we are converting a well-formed formula to CNF, which is okay, I get that. And we are assessing the negations. Do we start from the inside and work our way out? I work the negation from the outside in, not from the inside out. Because, you know, eventually you want the negation to only apply to variables and not parenthesized expressions. So you want to work the negation from the outside in, and DeMorgans Law is the trick to do it. All right. So with the example that you're giving me, you basically apply I would do the outer one. I mean, this one is easy because you basically just end up with a double negation of P or Q. You know, for people who want to know what we are talking about the example in the text channel. So this is basically just a double negation of P or Q, which means we just get P or Q back. Okay, so let's go back to here. All right, so the next portion is a little bit interesting, okay? So this one, you know, shows that what about this, okay? We are defining psi as a gigantic conjunction of all of the elements in iota. That's basically what this is saying, you know, because if you look at this big AND operator, it's kind of like a sigma, okay? You know, I'm using this as a sigma notation, and what we are ANDing together, each one is E, you know, each expression that we're ANDing is just E itself, and what E is an element of iota. So we are taking every single well-formed formula that is known to be true, and then we just make one gigantic conjunction out of it. Okay, that is psi. Okay, psi is this is how psi is defined, and then phi, on the other hand, is the theorem that we want to prove. Okay, so somebody gives you a quote-unquote random statement. Okay, you know, a bunch of ands, ors, you know, implications, and whatnot. Okay, so we want to prove that we want to know whether phi is a theorem or not. So we need to take a pause right now. Okay, what does it mean when we say, you know, is phi a theorem based on everything that is known to be true in iota? What does that mean? What that really means is we want to know whether psi implies phi or not. That's it. Okay, so if I go back to the tablet, okay, psi is a conjunction of all WFFs known to be true. Okay, and then psi is a statement. Okay, when I use the word statement, it really just means is a Boolean expression. Okay, so we'll just say this is a Boolean expression. So if psi implies phi, then phi is a theorem. That is basically what a theorem means, is it is implied by all the things that are known or given to be true. So we'll stay here for a little bit. Do we have any questions? Okay. So I'm getting back to the text channel. So for stuff like this, we can probably do this maybe at a certain time, because it's not exactly along the flow of the lecture at this point. But the answer to that question is it doesn't matter. Okay, you can apply the outer one first, you can apply the inner one first, it doesn't matter. Okay, the idea is you want to get rid of the negation of a particular operator. That's the bottom line. Doesn't matter which way you do it. Alright, so getting back to the lecture. Okay, so getting back to the lecture, this is how we define whether something is a theorem or not. Okay, because it depends on whether it is implied by everything that is known to be true, and we start with everything that is in iota. Okay? So do we have any questions about what a theorem means in the context of propositional logic, which actually is kind of the same in all of your math classes? If you ask any math professor and ask, what exactly is a theorem? They will give you a similar answer, but probably using different terms. So go ahead and think about, questions. And I'm going to start a new page on the tablet. Okay, so do we have any questions at this point? Not seeing any questions related to the lecture. So what I'll do is I am going to continue. Okay. So this part here is basically saying, what if psi implies phi is true? Okay, what does that in return implies? In other words, if phi really is a theorem, what does that mean? So now we use the corollary that we have been talking about. Okay, so basically what we are doing here is we're saying, remember the R. Okay, let me go back to the tablet, or actually I can just kind of show this part here. Okay, I think I can show both at the same time. If I just zoom out one level, that should do it. Right. So let me scroll up. There we go. So you can see how P is kind of like psi, and then Q is kind of like phi, right? And then what is R? What is this R over here? It is not phi. Okay, because there's no restriction of R, what R can be. R can be something totally unrelated to P, Q, okay? But R can also be derived from one of those two. So, having not phi taking the place of R here is actually perfectly okay. So the first, this thing implying the second row is because of the corollary. The corollary. Okay, so I'm having problems pronouncing this particular word. Corollary. So my tongue just doesn't roll. Doesn't roll conveniently for this word. But this corollary allows us to go from the first row to imply the second row. So now what does it mean? From the second row to the third row is really just looking at phi and not phi, and go like, hey, tech, that is just false, right? Because phi, if phi is true, then not phi is going to be false. If phi is false, then not phi is going to be true. But one of them is going to be false. And since they're connected by a conjunction, that means the conjunction itself has to be false. So that means psi and not phi implies 0. Okay, let's think about this for a little bit, okay? Because what does it mean when we say, psi and not phi implies 0? And that implication is going to be true. So what does it mean when this implication is true? What is that telling you? We already know the consequent is false. So what does the precedent has to be in order for the consequent to be false? Okay, let me rephrase that. That was a bad way of phrasing this. If we already know the consequent, which is the right hand side of an implication, is false, and we know the implication itself is true, what has to be the value of the precedent, which is the left hand side of the implication? If you look up the truth table, the answer is right there. If you look up the truth table of implication, the answer is right there. So I'm waiting for someone to type the answer because, based on what you already know about implication, you should know the answer already. So let me just repeat what we already know, the conditions. The condition is we know the implication itself is true. We also know the consequent is false, and we want to know, does that lock down the precedent? The precedent is going to be, it has to be false. It has to be false. Okay, so let's go back to the tablet. I'm going to show you how to reason this out. Okay, all right. So basically what we have is we have a question mark implies false, and we know this thing is true itself. We know the implication is true. We also know the consequent, which is the right hand side, is false. We're just asking, does that kind of lock down the precedent or not? Okay, a antecedent should be right, and then precedent should be false. Okay, antecedent or precedent. Okay, so the way we look at this is to look at it as a truth table. So we got x, we got y, we got x implies y. This truth table was introduced, I think, in the first class. So we have 0, 0, 0, 1, 1, 0, and then 1, 1. And then by definition, x implies y is going to be true whenever x is false. Okay, so 1, 1 over here. This is the only time the implication itself is false, and then this is when the implication is true again. So this is a truth table. So based on this truth table, since we are talking about the implication itself is true, so that means we are basically looking at one of these three rows. Potentially, we may not be able to lock down one of them, but we'll see, right? So when you look at these three rows, we also know that the right hand side of the implication is false. So out of these three rows, we can see that this one here is the only one that meets all the requirements, because it meets the requirement that the implication itself is true. It also meets the requirement that the right hand side of the implication is false, because for the other two rows, this one and this one over here, the right hand side of the implication is true. So now we know that we are just locking down to one single row, which means now we know that x has to be false. The left hand side of the implication has to be false. Okay, so what does that mean? Right, so what it means is, let me go back to the browser. So what that means is this conjunction has to be false. If phi is a theorem, then this conjunction has to be false. And that really is the basis of proof by contradiction. So I'm gonna pause here so that you guys have a chance to think about this and potentially ask questions. No questions, or you guys are still thinking? I cannot tell. Okay, still processing. I think we need an emoticon that is an hourglass and make it animated, because old computers, Windows, has an hourglass that keeps flipping. I don't know why they got rid of that hourglass icon. Yeah, exactly. But it doesn't animate. We need something that animates. So we have more distraction in life. Hmm. All right. So Jack says it makes sense. Anyone else? Okay. Oh, okay. So here comes Angel. All right. Um, a contradiction means everything that is known to be true as a conjunction is contradicting with um, the negation of the theorem because this conjunction is false. They cannot be true at the same time. Now, if they cannot be true at the same time, and we already know that everything that psi is representing everything that is known to be true, um, so the conclusion is phi itself has to be true if this whole thing is false. In other words, to answer Angel's question more directly, the negated proposed theorem is contradicting everything that is known to be true. We'll look at an example. Okay, we'll look at an example to show this to understand what this means. So we expect it to be false, but prove it to be must be true. No, okay. So it depends on how you look at it. If you are given a theorem and you're told to prove the theorem, so what you're doing is by negating the theorem that you're supposed to be proving, um, you want to make a conjunction out of the negated theorem and everything that is known to be true, and then see how that cannot be the case. Okay, that's basically what a contradiction is how that cannot be the case. All right, so let's look at an example. Okay, let's look at an example that has nothing to do with resolution, because proof by contradiction is really just a technique of mathematical proof, and it doesn't have to be applied to resolution. And we are just using it in the context of resolution because we're dealing with propositional logic. So in this case, in 5.4.1, I am introducing a pigeonhole principle. Okay, so you can click on this link, and I think it goes to a Wikipedia page. There we go. So it's a pigeonhole principle, which basically means, if you have n items to put into m containers with n is greater than m, then at least one container must contain more than one item. That seems to make sense, right? Intuitively, it makes sense. Okay, let me say that one more time. Let's use an example, okay? And I got a call. Okay, okay, so let's use an example here. The traditional way to look at this is to look at pigeons. Okay, so you have more pigeons than there are pigeonholes. So when the pigeons come home, the idea is at least one pigeonhole is going to have more than one pigeons in it. Okay, that's the theorem. That is the statement. So it makes sense, right? It makes perfect sense. It's like, okay, what about this, right? It is so obvious. And then I say, prove it. You go like, why do we need to prove something that is already intuitive? It's just right. I mean, it cannot be wrong. Then I go like, prove it. They go like, okay, we can. This is so simple. This is so intuitive. It has to be easy to prove. Well, as it turns out, proving it in a positive direction is actually difficult. But using proof by contradiction, it is actually relatively easy. So now let's go ahead and take a look at the proof using proof by contradiction. So we'll go ahead and go back to, oh, not there. We'll go back to the notes here, which is this module. All right. So the hint is negate the theorem first. Remember, the theorem is phi, and we want to combine negated phi with psi. So we want to negate the theorem. So the theorem is basically saying if n is greater than m, then at least one container is going to have more than one pigeons in it. Okay. So when you negate it, it becomes okay. Let me see, where's the negated theorem. So the negated theorem in this case is basically saying, given that we have more pigeons than pigeonholes, okay, there's a way to arrange it so that every single pigeonhole only has up to one pigeon in it. That is the negated theorem. Let me say that one more time, okay? Let me relate those two things. The theorem that you want to prove, okay, is the fact that if you have more pigeons than there are pigeonholes, then at least one pigeonhole is going to end up with more than one pigeons. That is the original theorem. But when you negate that and say, no, that is false, okay? When you negate it, then it's basically saying, there are more pigeons than there are pigeonholes, but there is a way, there's at least one way to arrange it so that every single pigeonhole has at the most one pigeon. Okay, that is the negated theorem. So now you look at the negated theorem and go like, okay, how can that be wrong? Okay, let me switch to the tablet because I think it's helpful to kind of write this out. Okay, so the negated theorem is saying, we have, I'm not going to use complete sentences here. So we have more pigeons than pigeonholes. And then there exists a way to arrange pigeons such that every pigeonhole has at the most one pigeon in it. That is the negated theorem. So now we have to show how the negated theorem cannot be the case. Okay, how it is contradicting everything that is known to be true. All right, so here we go, right? So we can basically use n to represent the number of pigeons. We use m to represent the number of pigeonholes. Okay. So what the negated theorem is going to imply is n is going to be less than or equal to m. Does that make sense? Because we have m pigeonholes and we have at the most one pigeon in each pigeonhole. So that implies the number of pigeons is less than or equal to the number of pigeonholes, right? But this, so when you look at this, okay, this is basically, this here is not phi, okay, in terms of the terminology that we have been talking about. So not phi is going to imply n is less than or equal to m. But when you combine this, okay, when you combine n is less than or equal to m, and you combine it with everything that is known to be true, what is known to be true again? N is greater than m. That is false. So this is how we basically, that concludes proof by contradiction, because the introduction of the negated theorem, and when you combine that with everything that is known to be true, which is we have more pigeons than there are pigeonholes, end up with a contradiction because it is false. Oh, probably shouldn't use this symbol because I should use this symbol here because that can help us differentiate a false versus what we use for phi as a Greek letter. All right, so I'm not sure whether people have questions about this or not, and I'm looking at Tom's message. Oh, because one whole can have 0. Exactly. So this is proof by contradiction, which is a very counterintuitive way to prove something. But in many mathematical proofs, the forward way of proving is actually much more difficult compared to proof by contradiction. All right, so I'm gonna take a pause here and see if there are any questions about this example of proof by contradiction. If you guys want to, I can make another one. Yeah, I kind of guessed people would like that. Okay, that's good. Let's do another one. Okay, so the next one is going to be a little bit more math oriented. Okay, so I'm going to use mathematical symbols in this case because I can. The pigeonhole one is kind of like, it's not that easy, but this one is actually doable. So we'll say, for all A, B, C as natural numbers, okay, the following has to be true. Okay, so the following is going to be, I'll say A times B equals to C implies A is less than or equal to the square root of C, or B is less than or equal to the square root of C. And put extra parentheses, so that everything is clear. This is our phi. This is the proposed theorem. So before we move any further, I want to make sure that people understand what this means. So go ahead and check this out when I try to answer a particular email, because I just got an email in that is kind of important. Oh, okay. I might have used the wrong setting. Okay, how about that? Daniel, can you hear me? Okay.
Working now. Thank you.
Okay. Yeah, I muted you a little bit earlier because we on Discord we can all hear you or what is in your background, and so I muted you, which should not prevent you from hearing me. So I'm not sure exactly what is going on. Okay. Um. Okay. So this is our phi. Okay. This is the theorem. So now the question is, how do we prove this is the case? So let me give you a few examples first. Okay. We are mostly concerned about A times B equals to C, because if C is not a product of A and B, then the left-hand side of the implication is false, which means the implication is going to be true anyway. So those cases do not concern us. The cases that actually concern us would be the cases where C really is the product of A and B, and then all three, A, B, and C, are all natural numbers. Okay. So we can think of a few examples. So I'm going to use 9 equals to 3 times 3. So this obviously meets the requirement because 3 is less than or equal to the square root of 9. 3 is less than or equal to the square root of 9. So both of these less than or equal to are true in the case of 9. Let's try something else, right? Let's try 20. So I can express 20 in many ways, but this time I'm just going to use 4 times 5. So when you look at 4 times 5, you can say A equals to 4, B equals to 5, and then C equals to 20, and then plug those numbers into this portion here. The square root of 20 is 4 point something, right? So that means, a is less than or equal to the square root of c is true. So since this is a regular OR, if at least one side is true, we're done. Okay, so we can definitely see that the theorem is true for the case of 20 equals to 4 times 5. And then you can spend all day trying to find a counter example to basically show that the theorem, which is this part here, is false. And then you will not find a single case. But not being able to find a counter example is not a proof. Okay, just because you can say, okay, I tried all day long, and for every single case that I tried, this theorem seems to hold true, and therefore the theorem is true. That itself is not a proof. Okay, you cannot submit that as a proof. So what are we going to do? Well, we can prove by contradiction. So now we want to first talk about what is not phi in this case, which is pretty easy to write, okay? Because what I'm going to do is I'll do it the lazy way. So doing the lazy way means I'm going to use the selection tool, and we are just going to take this whole thing, right? And copy that into the same document. And then we'll just move it around until it is next to the negation operator. I think the negation operator is about here. Oh, not quite. Move it a little further. There we go. This is a good spot. Alright. So not phi. Oh, I need to switch back to the writing tool. So not phi is really just the negation of this gigantic thing. Then go like, oh man, what are we going to do with this, right? Now, if you remember, the discussion of quantifiers, the one thing about quantifier is if you want to say it is not the case for all x, p of x. Okay, I hope you guys kind of sort of remember this, and I'll make sure that this negation is applied to the for all. This really is the same thing as there exists at least one x, such that it is not the case p of x is true. Okay, so I hope you remember this. How many people still remember this? We talked about this a long time ago, when we talked about quantifiers. Okay, so yes, so in this class, almost everything kind of is related to everything else. So you kind of have to keep everything in your mind, or at least have a handy place to look up the definitions. Okay, and look up everything that you have learned so far. So assuming that you guys remember this, now we apply that. Okay, so if we apply that, that means this negated phi can now be rewritten as there exists a, b, c in the set of natural numbers, such that it is not the case that a times b equals to c. Oops, extra parentheses not needed here. A times b equals to c implies. Okay, I'm just copying the rest here. I could have used the copy tool, but this seems a little faster. So I close this, close that, and then close that. There we go. All right. So I just applied, this. I just applied the negation of a for all can be converted into a there exists, and then negate the predicate instead. And I just applied it here. So now, what do we see? So the key here is the quantifier is really just saying that all I need is to find one case. Okay, if I find a single case, of choosing a, b, and c as a natural number, such that this portion is true, then I'm set. Okay, all I need is to find one case. So the focus is no longer on the quantifier. The focus is now on this side here, and basically see how that would not be possible. So the negation here is applied to a implication, which basically means now we have to do a whole bunch of linear algebra, Boolean algebra stuff. So we'll go ahead and do this on the next page, because there's not enough area in this page to do this. So what I'm doing is I am just selecting the portion that I need to copy to the next page. So we'll go ahead and do a copy. And then start a new page. And paste it into the new page here. There we go. Alright, so we'll start here. And change back to my writing tool. And now we say, what can we do with this? So this is another application of Boolean algebra. Okay, and to answer, the question that Aiden probably is having in his mind is, yes, we can do this using a truth table too, but we're going to do it the hard way. We're going to do this the hard way and use Boolean algebra. All right. So the first thing we do is we try to get rid of the implication. So we negate A or B equals to C first, and then say this thing or, and then whatever is on the other side is just preserved. So we will preserve that entire side, which is A is less than or equal to the square root of C, or B is less than or equal to the square root of C. So now let me match the parentheses. I think I'm missing one. Nope, I did not. Okay. I think I did miss one. Yep, I did miss one. Okay. This parentheses doesn't belong here, and instead we need one all the way to the end, because the negation, this negation here is applied to this or over here. So the next thing we do is, we don't like negating, an operator. Okay, so we use DeMorgans Law. Okay, so when we apply DeMorgans Law, we are distributing the negation to the inside. So by doing so, the or becomes an and then we negate every single component. So we have the negation of A times B equals to C, which is basically just saying that C equals to, oh, I used double equal, but it's the same. Okay, it means C is the product of A and B. And then the next thing we do is we negate the other side. Now we have a negation applied to A is less than or equal to C, or B is less than or equal to the square root of C. And let me just double check, make sure the parentheses all match up. Yep, okay. So you go like, you got rid of one situation where you have a negation applied to an operator, and then you created another one because this negation is applied to this or now. Okay, so once again we have to use DeMorgans Law. So now we say, okay, fine, let's see what we can do. The first thing we can do is to get rid of the double negation. So now we just get A times B equals to C again. And this and stays here. And now we go like, it looks like we can apply DeMorgans Law again because we have a negation applied to an or. So let's go ahead and apply that DeMorgans Law. So now we have the negation of A is less than or equal to the square root of C, and it is not the case that B is less than or equal to the square root of C. Okay. Are we good so far? Okay, I'm not seeing any text in the text channel. Yep. Okay, so we can do a few things, that are just normal algebra stuff. Okay, so we can now say A times B equals to C, and okay, so this pair of parentheses can dissolve because of the associative law of conjunction. Okay, because it doesn't really matter how we nest if we just have a whole bunch of conjunctions. So now we just say, this says it is not the case that A is less than or equal to the square root of C, which is easier to say when we just convert it to say A is greater than the square root of C, right? So Aiden is correct. We take the negation of less than or equal to, and then turn it into just greater than, which is it means the same thing. It's just a whole lot easier to read and to write. So now we do the same thing over here. B is greater than or greater than the square root of C. Now I think some of you are noticing and go like, oh, so this is why. Okay, and others may be going like, I'm not seeing any problems here. This looks okay to me. So what we're going to do is to say, okay, we know the relationship between A times b equals to c, right? So we know that. So now we say, but we also know a is greater than the square root of c and b is greater than the square root of c. So we take only this portion and then we say, this implies a times c is greater than the square root of c times the square root of c. Because everything is non-negative. Because a, b, and c, they are all natural numbers, right? So we don't have to deal with, oh, but the sign is flipped and we cannot do the multiplication. We cannot maintain the inequality after we multiply things together. Okay, that happens when you can have positive and negative values, but since we're only dealing with non-negative values, so we can take a from this side, put it here. Okay, so let me just draw the arrows. So a goes here, b goes here, and because a is greater than the square root of c, that goes here, and then the square root of c goes here. That's just normal, algebra for inequality when you're dealing with numerical values. Okay. Then you go like, okay, that means a times b is greater than c, right? Because the square root of c times the square root of c is c itself. Can I multiply Boolean equations like that? Not really sure what you mean by that. Multiply Boolean equations. You mean distribution? Okay, so we got Aiden and Jack both typing at the same time. Okay, so this is not Boolean algebra. This one is it has to do with just regular algebra. I'm not really sure what you mean by similar in Boolean algebra. So maybe we'll take this one off, quote unquote, offline, after class. And I know that Jack was typing a little bit earlier. Maybe there was not a question anymore. Okay. So now we say, oh, but now we have a problem because on one side we have a times b equals to c, which is, this is coming from psi. Okay, this is coming from what is known to be true to begin with. And now we have the other one, which is a times b is greater than c, which is derived from phi, from not phi. Okay, this is implied by not phi. Not phi implies this. And when you look at this, the whole thing is false, right? Because, okay, I have to be careful how I write 0 because I don't want the stroke to get through the circle. So now we have the proof because the negated theorem, which is basically this part here, this is the negated theorem, eventually, becomes, okay, this is negated theorem, but eventually it becomes contradictory to something that is given to be true, which is, a times b is in fact the product. A times b, the product of a and b is c. And now we have a contradiction. So that concludes the proof by contradiction because we can see how not phi leads to false. Okay, so Angel is typing, and when Angel is typing, I can also talk a little bit about the application of this particular theorem. Why do people care about this theorem? But I'll answer Angel's question first, so the rest of you can kind of think about what is the application of the theorem that Tack has just proven. Why does it matter? What is the importance? I mean, I do talk about things that are not important all the time, but this one is not one of those. And also, I want you guys to kind of think about, oh, okay, there we go. So Angel's question is, since these are Yeah, we are not dealing with imaginary numbers because imaginary numbers cannot be compared. I do not think they can be compared. They're not totally ordered. So there's no comparison that can be done. And the premise is A, B, and C are all natural numbers, so that is not an issue. Yes, they are partially ordered. Yeah. All right, so now we get back to the point of okay, there are two things that I want to talk about before we are running out. We are not running out of time. We still have 20 minutes, so I can talk about both of those things. So the first one is what is the application of this? Okay, the first application is when can you declare a number as prime? Okay, so we are now dealing with factoring. So I'll give you an example. Let's look at 101 in base 10. Okay, I know 101 looks like a binary number, but no, this is actually a base 10 number. Let me just emphasize that we are looking at 101. So 101 is a prime number. Okay, but if you ask, let's say, an elementary schooler and go like, okay, tell me whether 101 is prime or not. Okay, the elementary schooler would probably understand, and then you have to kind of define, what a prime number is. Is the number is divisible only by itself and 1. It cannot be divisible by any other natural numbers, right? Okay, so the elementary schooler would go like, this sounds really kind of tedious. What do I get if I finish this? Go like, maybe a candy. Okay, so now the elementary schooler wants that candy and go like, okay, I'll do it. So they would go like, okay, 101 divided by 2 is 50 with a remainder of 1. 101 divided by 3 is what? 33 with a remainder of 2. 101 divided by, so since we're talking about elementary schoolers, they may just keep going with 4, right? They don't know that they can skip composite numbers or products already. So they'll go like 4, okay, it is 25 with a remainder of 1. Now, I know it takes up extra time, but it's not wrong. Okay, you cannot possibly misidentify a number as prime or not prime. You cannot come to the wrong conclusion because you test 101 with 4. So now we go like 5, which is the super obvious one, 20 with a remainder of 1, and so on, right? So an hour later, the elementary schooler goes like, okay, I get to 101 divided by 10 is 10 with a remainder of 1, and then 101 divided by 11 is 9 with a remainder of 2, and so on. So at this point, you step in, and then you gave the elementary schooler the candy. Right at this point, okay? Right when this one is confirmed. Okay, then you go like, okay, here's your candy, good job. And the elementary schooler goes like, the other elementary schooler, the ones that are not done yet, will go like, that's cheating. We're not done yet, because we're supposed to go all the way to 101 itself, right? Because we want to prove that 101 is divisible only by itself and 1. So we're going to go 11, 12, 13, 14, all the way up to 100. And then by the time we get to 101, obviously 101 divided by 101 is 1 with a remainder of 0. Then we are done. Only then we are done. You go like, nope, we're done here. Once we try 11, and 11 is not a factor of 101, we're done. So now can you as a college student realize why that theorem is useful? In fact, once you're done with 10 and you realize that 11 is greater than the square root of 101, you're done. You don't even need to know that 101 divided by 11 has a remainder of 2. You don't even need to get there. You just need to know that 10 is not a factor of 101, and 11 is greater than the square root of 101. But can you make the connection now? Why the theorem that we talk about, is useful? Because if 101 is not a prime number, we would have found one of the factors by the time we get to 10. The fact that we did not find a factor up to 10, and the next number is already greater than the square root of 101, means that it does not have a factor other than 1 and itself. That is why we can stop. Are we okay here or not? Let's go back and look at the theorem. It says A times B equals to C, meaning C is the product of A and B, implies A is less than or equal to the square root of C, or B is less than or equal to the square root of C. That is the theorem. In this case, we are dealing with C being 101, right? And we want to find all the factors. Now, 1 is an obvious one, and we're not going to deal with that, right? So other than 1, can we find any other factors? So we try 2, doesn't work. We try 3, doesn't work, and so on. So by the time we get to 11, then we have already tried everything. Anything that would have worked would have been found already by the time we got to 11. But since we did not get anything, that means that is already telling us that 101 does not have any factors other than 1 and itself. Does that make sense? I'm trying to see if people can either confirm or not. Okay, thank you. Very good. Thank you, Aiden. Aiden P versus Aiden A. Very good. Okay, so we are getting it. Good, good, good. But this particular theorem, can be proven using proof by contradiction. Okay, basically you're just saying, let's say the theorem is false. Let's see what can happen. And then it just leads to contradiction, because basically it cannot be. Okay, then we get to the solution. All right, so let me just kind of we have 15 more minutes or so for the lecture, but I want to do a quick recap first before I give you the role taking activity. So the recap is basically saying what do we have at this point, right? So what we have at this point is the mechanism of resolution. And what exactly does it look like? It basically says our entire zeta, as a set, has one single rule. And that rule says, give me something that looks like this. Okay, we have psi. Now this psi is not the conjunction of everything in iota. This psi is really just a schemata. It's really just a placeholder. So we have psi or, okay, I know I'm not using the same Greek letter as last time, but it's okay. And then comma, not theta, or rho, okay. And this infers the concatenation of psi or rho, okay. I just have to make sure that I close the braces correctly. This is the entire zeta, okay, not counting the ones where we dissolve parentheses and stuff like that. But the only really meaningful rule is this one. This is resolution, okay. So this is the first ingredient. The second ingredient is basically saying, let's see, define. Okay, so in this case, I'm defining. I probably should not use psi, so I'm going to use another Greek letter here. Let's use alpha. Okay, so I'm defining alpha as the conjunction, the gigantic conjunction of everything in iota. Okay, so we define this as alpha, and then we say, oh, I can use phi now. So if alpha and the negation of phi is false, then phi is a theorem, which basically means phi follows everything in iota. Okay, so this is the second piece, which is the piece that we just talked about today. Resolution we talked about on Monday, and then this is the second piece that we just talked about today. So now the question is, I don't see anything connecting these two, right? How do they connect? So what I want to do is to say, okay, let's take a look at a particular resolution. Okay, so we'll say, what if we know P and not P? Okay, what does that do? I put extra parentheses here because I only want to use resolution. Because all of you, not one, but all of you would just point out to Tech and say, Tech, we looked at this a few pages back, on the tablet, because this is one of the rules that you say, we can simplify. P and not P is just false. We are done. What if I say, don't use any one of those rules? The only thing you can use is resolution, which is this thing here, right? Then you go like, it doesn't apply because we don't see any disjunction here. Yes, you do. Now we have disjunction, don't we? In other words, every single term in the conjunction can have an implicit or false in it. Most of the time we don't write it out because it doesn't do a single thing. But if we want to say, but we are sticking to the application of this rule here, and it has to be a disjunction in order to apply this resolution, fine, we'll make it a disjunction. Okay, we'll make it a disjunction by saying or false. Now it is a disjunction, right? And some of you will go like, okay, so what can we do now? So now we're basically saying each one of these is a well-formed formula that is known to be true in the system, this one and also this one. The conjunction is implicit when we use resolution. In other words, this comma, which is basically separating elements in a set. This comma is basically implying we have a conjunction because everything that is currently known to be true are ended together. They are all true at the same time. Okay. So now we apply resolution. So when we apply resolution, we identify the theta in this case to be P, and then not theta to be not P. So when we apply the resolution, we end up with whatever is left from one expression, or whatever left in the other expression. So now we end up with 0. Okay, let me just change this. This infers 0 or 0. Right? So 0 or 0 is just 0. So that means this is just false. Are we good so far? Does everybody see how I applied resolution when we get down to just P and not P? So instead of using Boolean algebra, which is what you need to use in the current homework assignment, I use resolution, which is what this rule is saying. So are we good so far? Maybe, maybe not. Alright, so there's an example. At the end of the module, there's an example. There are two examples, in fact, to illustrate what you can do. Substitution? Well, resolution is not exactly substitution. It is just symbolic manipulation. If you identify, a variable in one, and you identify the negated version of the same variable in the other one, then you can concatenate the rest of each of these two disjunctions and get rid of the variable that is negated on one side and non-negated on the other side. So it's a concatenation mechanism, more like a kind of mechanical syntactical operation instead of a substitution. I don't understand what we took from zeta to make the current equation, or how we took it. So this is just an example. This is an example of, when we end up with P and not P, how do we use resolution to arrive to the same conclusion that we have false. So that's kind of what we did, Evan. And then Anita said, so in zeta we have theta, and in the proof we have 0. Oh, okay, I see. Okay, so um, when we apply a rule, yes, so there's a certain amount of substitution going on. This is a pattern. Okay, this part here is specifying a pattern. It's basically saying, of all of the well-formed formulae that are known to be true, can we find something that looks like this and something that looks like this? Okay, they both have to be disjunctions. But the most important point is one has a non-negated thing and the other one has the negated version of exactly the same thing. So this is basically identifying a pattern for us to match. Once we match the pattern, because we say, hey, P or 0 matches this pattern, while not P or 0 matches that pattern, then we fire the rule, the production, and then we end up with a new thing, which is on this side, which is basically the OR concatenation of what is left of each of the original expression. So since we bound psi to this 0, and then we bound rho to this particular 0, so we end up with just 0 or 0 on the other side. Okay. Oh, don't forget about rho taking. Sure. Okay, so we're going to take rho today. We'll do it now. Yeah, sure, absolutely. Let's take rho, and I do have to emphasize to the class again that you have to participate in the rho taking activity, because this is how I go to the grade sheet in Canvas and know who attended the class or not. So it is really important that people participate in the rho taking activity, because 3 or more absences is considered excessive, and that can be a reason to be dropped. And that applies to people who are going like, but I was on Discord. Well, I'm not taking a snapshot of Discord while I'm teaching. I cannot do that. So the only way I can do to see whether people were present in class or not is to go through the rho taking activities. So that's why it is really kind of important to do this. Alright, so we'll put this into the rho taking group, which means it doesn't count for grade. So technically speaking, I do not, for rho taking stuff, it doesn't count to points, for your grade. And that really is the policy of, I think, every single UC, and I think CSUs have similar policies, that only academic stuff can count to a grade, and rho taking is not academic. So we'll go ahead and we'll do the questions first. Okay, this is the fun part, because all of you are thinking, what is TAC going to use as the word for today? So what word is TAC using for rho taking? And I think some of you probably can guess it already. It's Pigeon. 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 Lowercase. So we'll go ahead and update question. Make sure that we have not multiple choice. That wouldn't be fun. So fill in the blanks. Update question. And then we go back and set up the time. So I'll give you guys, as usual, until 1:30 to turn it in. So March 10th, 1:30 p.m. March 10th, 1:30 p.m. And then save and publish. There we go. So the word for today's road taking activity is pigeon. And you have to spell it right too. Pigeon, pigeon. Hmm. Okay, there we go. All right. So I'll give you guys a few minutes, so that you guys can get this out of the way right away. Good one, Naji. Alrighty. So let me go back to the module. So for those of you who want to know the application, because we only got about 1 minute left. So for those of you who want to really connect all the pieces together, in today's lecture, just kind of go all the way to the example. Okay, there are two examples um, where I would use one statement for psi, which is basically everything that is known to be true, except in this case it's not in CNF yet. Okay, so the first thing we need to do is to turn it into CNF. And then I'll propose a particular statement. In this case, phi is not t implies p. Okay, and I want to know whether this particular phi as a Boolean expression is implied by psi. Okay, in other words, is this phi here a theorem? So the first thing we need to do is to invert, or not invert, but to negate the proposed theorem, in this case phi, and turn it into a CNF. So the CNF corresponding to the negation of phi is not t and not p. And then we combine these two. Okay, so we combine psi, which is everything that is known to be true, and the negated theorem. So we end up with this. So now we try to apply resolution. And as we apply resolution, in this case, it is not applicable. Okay, there's no resolution that can be applied because the pattern of resolution does not match. Doesn't matter which two sub-expressions you're talking about, they simply do not match. You cannot find a variable in one and the negated of the same variable in the other one. So since you cannot apply resolution at all, we cannot make the conclusion that phi is a theorem of everything that is known to be true. So now we have another one, which is phi prime. It is defined as p implies not q. Just like the other one, we turn it into a CNF first, and then we combine the CNF and of the negated theorem with everything that is known to be true. And then this time I use underscore to identify what variable I'm using for resolution. So I pick this one, and then they end up with just not q by itself. And then we combine the q and the not q, and that becomes false. And as a result, we have our answer. Okay, because when the conjunction between everything that is known to be true and the negated theorem, when that conjunction is false, then using proof by contradiction, we know that phi prime in this case is in fact a theorem. It is implied by the everything that is known to be true in iota. So that is fairly good timing by my standard. I'm only 1 minute and a half over. um, and that's it. That's it for today's lecture. You still have a homework assignment due on next Monday, so get on that one, okay? Because it's interesting because you're using Boolean algebra, but at the same time, if this is like your first time using Boolean algebra, that can take a little bit of time too. So don't wait until the end. Don't wait until like Sunday to get started. Aiden asked, where do I get the negated q? So this negated q is because of the application of resolution. So when I take this, not p or not q, and this one which is just p itself, which is implied to be p or false. So when I perform resolution, so these two resolved will give me not Q. That's where not Q is coming from. Does that answer the question, Aiden? I resolved not P or not Q, and then P by itself is sort of like P or false. So P versus not P, those two are used for the resolution. And then when I concatenate, quote unquote, the rest of each expression, I have only not Q left, because P does not really have the rest, quote unquote, the rest of the expression. So that's why I'll end up with not Q. Okay, all right, there we go. Cool. Okay, so we are done with today's lecture. I will stay online for maybe a few more minutes, to answer any questions about today's lecture. But I'm gonna turn off the streaming. So everybody have a nice weekend. Okay, have a nice weekend. Yep, it is Wednesday. It's only Wednesday, but for us, our next class meeting is Monday. So have a nice weekend.